I will talk about the observation and the data analysis part and the result section. And I will end with the summary and conclusion part. So, whatever the respective speaker have mainly focused on the high mass star forming region, I will talk about the low mass star forming part. So, stars form inside the relatively dense concentration of the interstellar gas and dust known as the molecular clouds, mostly in the spiral arms of the galaxy. And star formation begins when the denser part of this cloud core collapses due to their own gravity. So as the cloud begins to contract, the density will increase, and as a result, Jeans mass will decrease. And so the core will collapse and fragment into the small clumps. This cloud will form into the protostars. This contraction and fragmentation will continue until the density of these fragments become optically fixed. So due to the energy liberation, the temperature will increase, and as a result, the Jeans mass will decrease and the further fragmentation will cease. So this is the brief about the pre-main sequence evolution of the protostars. So in the figure we can find this is the class 0 sources, which is the most youngest members. It has only envelope but no disk is formed. And the next part is the class 1 sources, where an disk is formed, and the near infrared emissions of the star may come from the thick envelope surrounding it. The next part is the class 2 sources, which is popularly known as the classical TW stars. And here the envelope is disappeared, and the near infrared emission of the star may come from the optical thick disk and the photosphere part. And the last part before the main sequence stars, main sequence is the class 3 sources, which is known as the weak line TW stars. And here the near infrared emission comes from the discrete photosphere part. Now I will discuss about the data sets. For my spectroscopic observation, I am taking the spectra from 2-meter Himalayan Chandra telescope. So for low resolution spectroscopic observation, we are using prism 7 and prism 8. And from slidless spectroscopic observation, we are using the prism 5 and prism 8 with H alpha Bodman filter. But in this electromagnetic spectrum, we can see that the whole part of the electromagnetic spectrum cannot be covered directly from the ground. So we have also taken some space-based observation to cover the near infrared and mid infrared region. So this is the archival data sets. Here for near infrared part, we have used the ground-based UTI DSS data, and for space-based near infrared data, we have used the WISE and Spitzer. The Spitzer covers from 3.6 to 8 micrometer region, and WISE covers from 3.4 to 22 micron. And we have also used the IFAS data, which is mainly called STOAN RI filter and H alpha narrow band filter. So this is my target region, SH287 or SH7. This is a 19 hours. This is a 19 hours object, and it belongs to the OB association. So we can see that here other two H2 region is also present. This is the SH289 and this is SH286, and our target is the SH287. This region is situated at a distance of 2.3 kiloparsec, and this region is not well studied. And one IRA source is also associated with this region. Okay, from the near infrared data, we have generated this extinction map. So first, I want to tell a brief about the generation of the extinction map. So we have followed the standard method of Buttermut et al. 2005. Here we have divided the target region into uniform bits of size 5 arcsecond by 5 arcsecond, and then from the center of each bit, we have determined 20 nearest neighbor sources, and then we have calculated the mean and standard deviation of the H minus K values, and we have estimated the sources of criteria 3 sigma, and then we estimated the AB using the standard formula mentioned here from Flattery et al. 2007 and Leakey University 1985. Here we can see that and now we had obtained the AB value, and using this AB we have plotted this visual extinction map. Here we can see that the AB value varies from 2 to 12 magnitude, and some of the part is really has a big has a high extinction of 12 magnitude. And this from this plot we can see that there is a non-uniform distribution of the extinction is present in this region. And from the histogram plot, we have estimated the median of value of the AV equals to 5.1. 5.12 magnitude. We have also taken the streetless spectroscopic observation using the HPOS instrument by Prism 5 and Prism 8. And from streetless H-alpha spectroscopic investigation, we have identified four new H-alpha emitting sources. And in the next slide, I will discuss about my slit spectroscopic observation and results. Before that, I have discussed the basic process of IRAP, which I have followed to extract the spectroscopic results. So this is the log of my observation. I have taken the spectra using Prism 8 up to massive sources, and by using the standard library and other previous literature, we have identified the important lines present and classified them as a V star that will help us to determine the cluster distance and other parameters. Okay, but from our streetless spectroscopic observation, we have not get enough H-alpha sources. So we have also used the IFAS data, and from R minus H-alpha versus R minus I color diagram, we have identified 20 H-alpha emission sources. We have just followed the standard method of Bernstein et al. And the source which belongs to the 3 sigma confidence levels of this green line, which is the CTTS threshold, are classified as the H-alpha emitter. Okay, so as I have mentioned, one of my objectives is to study the Freeman sequence sensors of the Freeman sequence stars, and color diagram are one of the important tools for this purpose. So by using the Spitzer data, we have classified class 1 sources and 42 class 2 sources. We have followed the Gutermuk et al. 2009, but the Spitzer has not sufficient detection in the all port band. So we have also used the WISE data, and we have followed the Koenig et al. 2012 for this classification. In the first plot, we have indicated all the contamination from past, swap, AGN, etc. And we have discarded all these contamination by using that Koenig et al. And finally get 70 class 2 sources and 20 class 1 sources. Most of them has already classified by Spitzer. So here we additionally get 19 class 1 sources and some about 38 class 2 sources from this part. So this is the brief summary and conclusion of my work. I have really done the multi-wavelength studies, starting from near infrared to the optical part. And by using the EQIDSS data, I have generated the extension map from where I get AV equals to 5.1 magnitude. I have also done the slit spectroscopic observation from which I have obtained the spectra of the massive stars. And from the streetless spectroscopic observation, I have obtained 4 H-alpha emission sources, and by using the IFAS data, I have obtained 20 new H-alpha emission sources. And for the mean infrared classification, I have obtained 70 class 2 sources and 20 class 1 sources from WISE data, and 42 class 2 sources and 1 class 1 sources from the Spitzer data. This is an ongoing work. I am planning to include others optical data and proper motion data for our future. So thanks for your time presence.
Thank you so much. One quick question. So you are using slit spectra and narrowband HFI imaging also?
Yeah, so actually we are taking slit spectroscopic observation with H-alpha broadband imaging.
Okay.
And from that we have identified 4 H-alpha sources. But we cannot increase the H to the time that we saturate.
Okay. So you have used the UK's data, right?
Yes.
So is there any condition one has to apply before using the data?
Yes, sir. I have used the Lucas squeeze method of as mentioned in the Lucas.
Okay.
to collect the data.
Okay, then this was the last talk of this post-lunch session.
Yeah, so thanks for being patient with these technical difficulties. So this is the end of today's session, and there is no break now because we are delayed by 15 minutes. So next talk will be by Professor Subramanian, and I will ask Isha Reddy to introduce.
Good evening. Welcome to this evening talk. Professor Subramanian. Can you hear me? Subramanian. She is the Director of Institute of Astrophysics, and also she is a renowned astrophysicist. Mostly, basically, she does observational astronomy, and she is also a fellow of National Academy of Sciences and fellow of Indian Academy of Sciences. And she's going to talk on UV missions, which was launched recently, one Astrocyte, and then one she's planning to. She's leading one of those next generation Astrocyte mission, that's the Astrocyte 2 kind of thing. Insist. And over to Dr. Subramanian.
Hello, am I audible?
Yes, yes.
Yeah, okay. Thank you so much for inviting me to give this talk. I'm really sorry for not being there and really miss being there. Unfortunately, I could not travel. And so I also thank the organizers to giving me a chance to talk to you over the online platform. So can I go ahead and share my slides for the presentation?
Yeah, sure.
Okay. Yeah, just give me a second. Yeah, are you able to see my screen?
Yes, yes.
Yeah, so since I was I'll be talking about the upcoming mission on astronomy, like the which is in the planning phase. But since it was mentioned as an evening talk, I thought I'll make it a little more put in a broader perspective and how we do astronomy and how things have evolved over a time scale. So I hope it'll be kind of cover the kind of diverse audience which is there as well. So I just thought I'll call it as astronomy from ground and space. So ground-based astronomy, we started from Galileo's time, and then he started pointing the telescope towards the sky and started giving us a lot more understanding about the universe, the kind of objects around us, etc. And then right now we have a large number of ground-based telescopes, and they are contributing to our understanding as well as contributing to a lot of data and new features regarding various objects as well as the new views of the universe every day. And the ground-based telescopes are in fact the workhorses of astronomical research. And to give you a picture is the 2-meter HCT and the night sky from there. But you put the telescopes at remote places, and we also know HCT and 3.6 meter DOT, and we operate these telescopes. And the important thing is that they are we can go there and make improvements to the telescope by updating it as well as improving the instrumentation of it. So you can go there and fiddle around with it. But the space telescopes you can't do. But then there are spectrum, part of the electromagnetic spectrum, which are not available in the ground. And you need to go above the atmosphere to get it. And so these are the main things which drive the space astronomy. And also, currently we know that in the last few decades, we know that many of our understanding regarding various objects come from multi-wavelength astronomy, as we've been discussing through this today's workshop as well. So you need to cover larger wavelength to understand the physical processes which are going on in various objects, starting from Youngster objects to star formation, to AGN, to various kind of stuff. So you need to cover the ground and the space together to get a comprehensive understanding of the physical processes and the universe. So we also know that the Great Observatories program of the US, which brought the wonderful 4 missions which cover the wavelength range from gamma ray to infrared, gave us a lot of understanding regarding various objects in the universe, and they span about 30 years. And we also know that the pictures we get from the same object look different in different wavelengths. And these have significantly contributed, and there are a lot of other missions as well, but these are the major missions which we should keep in mind. And they have made a substantial impact on astronomy by themselves, but Hubble being able to produce pretty pictures quite a bit, they have had a larger public and media impact with respect to the other telescopes. We know that the current, we are all looking forward to the JWST operations, which is launched in December 2021, and that is the near infrared, and this is the first multi-mirror telescope which is up in the sky, and it's kind of called as a successor to Hubble, but we should also keep in mind that it'll create wonderful images, but then that is in the infrared wavelengths. We will be losing the visible and the UV wavelengths capability that is there in the Hubble. Now, we should also see that when we are installing our ground-based telescopes based on the atmospheric seeing conditions and the number of clear skies, the space telescopes are put in orbits in various ways. Okay, I'll hide this. So there are there are main three types of orbits. One is the low Earth orbit, which is kind of up to a few hundred kilometers, and Astrocyte is in the near Earth orbit, so low Earth orbit. So that's about 650 kilometers. That gives approximately one orbit time of 90 minutes. That would mean that every 90 minutes, the Astrocyte would pass over Bangalore. And HST and ISS are also in the low Earth orbits. Many older missions are also placed over there. Now, there is also something called the sun synchronous orbit, where it is placed at a higher altitude, but then it goes from north to south, which gives a little more visibility to the night sky, and the antenna will be looking at the sun for quite a large time as well. So we propose this for the upcoming mission, because the efficiency of the coverage of the night sky per orbit would be larger. There is also long-range points, as shown over here, and the L1 and L2 are the more important ones. There are a lot of them at L2 already. Kepler was there right now. Gaia and JWST are there, and Euclid and WFIRST are also supposed to be put on L2, which gets a kind of a more effective coverage of the night sky. But though it's quite far away from Earth. The other point is L1, which gives more visibility of the sun, and then the upcoming Aditya L1 mission is supposed to go to L1. So these are the orbits in terms of space missions. Now, what does you need? You would also like to look at how to access data and also tools and techniques for each mission. So in order for the complete space mission to be complete and also utilized pretty well, and also quite easy for producing science outputs from the data which is put together by these space telescopes, the archives such as the MAST as well as the HESAC are playing a major role, because these are produced through data pipelines. They are calibrated and science-ready data is available. You can also mix and match. You just have to give the object name, and then it tells you what missions have observed these kind of objects, and the data is available for download. Not only do they give data from various missions, they also provide tools and techniques which are very, very important. Very important is like such as the Gaia tools. So they are really important for the user, for an astronomer or a scientist, to make use of this mission. So you don't have to go into the grand nitty-gritties of each mission, but then you will be able to use the data and do your science. And one of the recent activities are also being like people may need lot more space on their computer to actually run these tools, because the data you have downloaded may be quite large, and then tools have to run on them. But many of the sites also provide space where you can actually the data can be staged and you can do your analysis, and only the output you need to be downloaded to your computer. So these are also important things which should be available along with missions for their success in terms of producing science. So astronomy from space can be of various types. One is the high sensitivity deep fields, where you can look at the low mass star formation and the IMF, etc. You could also look at astrometric estimations for positions and space velocity, which are given by Hipparchus and Gaia, which actually help us to weed out the membership when it comes to clusters, space velocity, estimation of space velocity, positions, etc. High energy observations cover the other wavelength areas which cannot be done from ground. And of course, that contribute to the multi-wavelength studies. And UV also play a major role in the coverage. So rest of them are there. And there's one more thing which I wanted to mention over here, which is not covered over here, is the astroseismology part. Because if you look at Kepler and TESS, they have been able to produce light curves, and which were primarily meant to look at detecting exosolar planets. But then they've been, with their cadence, they've been able to also look at the small amount of low amplitude pulsations, which is able to probe into the astroseismology part of it. So that is also very important, which the space is able to provide. So many of these missions are very specific science cases, and also in many science cases, the science output is maximized by combining the data from ground and space. So it is important to have a synergy from ground and space together for advancing our understanding. And this is also not very new to the audience out here, because the multi-wavelength astronomy looks at various kinds of emission mechanism right from the coal to the hot gas. And it traces various aspects, and it is able to produce a comprehensive, holistic picture of the galaxy and all the activities going on out there. So also the tools, regarding particularly if you're looking at the nearby galaxy star formation, previously you would be looking at the UBV colors or a UE spectrum, optical, and then the CMD of resolved stars. But now we look at combination of galaxies, DSS2 mass, Spitzer, and also the gas, etc. So ALMA, VLA, etc. And also there are simulations which give you understanding of what is expected from these kind of physical inputs to the simulation, the models. So things have changed over the last few decades, and it is again important to have a combination of wavelength as well as combination of ground and space. Now, I just wanted to highlight a few results from Astrocyte, which I have been involved in. One is the FUV star formation in one of the recent galaxies, where we probe the reason for star formation, the inner and outer regions of the galaxy. You can see that the blue contour is the far UV emission, the red is the H1 column density, and also you can see the shells created by the supernovae eruptions or the OB stars. So the idea over here is that the central region seems to be the star formation is driven, or the episodes of star formation is to be driven by the shells, but then the outer regions it is not. So it is even in irregular galaxies, the feedback mechanisms do play a role, but then outer regions, it is not just this feedback mechanism, but also the environment tend to play a major role. There's another example where the UVIT image of the merged galaxy, this is the Atoms for Peace galaxy, where the tidal tails show star formation, and you can see the knots of star formation. And in this case, we had far UV and near UV together, using which we were able to actually estimate some ages. And that also helped in understanding the central regions of this galaxy, where you can see the yellow part at the center, which would mean that the deficiency of like the recent star formation, which would mean that probably Negian suppression is happening in the inner regions, which was unable to be produced from the HST image, which is already available. So resolution plus the wavelength does matter in probing specific aspects of star formation. As I mentioned, the Gaia mission, which has produced a huge amount of information regarding positions, prop motion, and parallax is effectively used to understand various stellar populations. And this diagram, using Gaia tools, people do the Gaussian mixture model to identify the distribution of stars, which tells you that there is a field star and there's a clump out there which relates to the cluster which is present there, and that can be used to understand various stars present in the cluster as well as the kinematics of the cluster. So Gaia indeed has revolutionary understanding of the nearby universe with astrometric and photometric data. And this is widely used for any studies with respect to nearby our galaxy or the nearby universe. Gaia information is very important. And this is also indeed a space mission. The other thing which people have been looking at is the multi-wavelength imaging, which is cheaper than spectroscopy. So that will help us to actually produce the entire spectral energy distribution and use for wide field surveys, where using which you can actually separate out binary stars. And so if you can put the deconvolve these SEDs to 2 stars, then you can actually not only estimate the temperature, but you can also estimate the luminosity, assuming the same distance to them. So if you know the luminosity and temperature, you can actually put them on the HR diagram to figure out what is the evolutionary phase of the binary component. So this as also indeed using multi-wavelength points as observations in the fields, within the clusters or in the field, to actually understand their binary nature. In this area, we have actually studied a number of Bluestragglers and old open clusters. This is a figure showing the Kalamanchy diagram of a globular cluster, where you can see the main sequence and giant branch and horizontal branch stars. But these are the Bluestragglers, which have somehow evaded to evolve into red giants. So the reason for them kind of evading the evolution is probably they acquired mass through a binary mass transfer process, or it could be a merger of 2 stars into one single star. So the idea over here is to, if you detect a remnant of a mass transfer process, then the mass transfer is probably the reason by which it formed. So again, as I mentioned, the deconvolution of the spectral energy distribution into a cooler and a hotter component was able to help put both the cooler and the hotter component in the HR diagram, and which resulted in identification of the hotter companion for a number of Bluestragglers and open clusters. The result being, it is actually indeed the mass transfer mechanism is at work in the production of Bluestraggler stars. But there was a surprise hidden out there, 2 surprises in fact. One is that people expected the remnant to be a normal white dwarf of mass about 0.45, which is the minimum mass one can produce from a single star evolution. But we were getting stars which are kind of less massive, of the order of 0.2 solar mass, which would mean that the stars which are, while in the red giant branch itself, the outer layer gets stripped off. So you are looking at the cores of the subgiant stars. So it would mean that the mass transfer at early stages, implication for their orbits. So that was seen in M67. We also see subdwarfs and HBs in another cluster. So, and NGC 188. So the result, the summary of this result is that we do see a wide variety of remnants, not just the white dwarfs. So which would mean that depending upon the masses of the components as well as the orbits, decide in the final product of this mass transfer. And this work is still continuing. And yeah, and we also see some of the stars which are on the main sequence to have transferred mass as well. And these we call them as blue lurkers. We have also completed the globular clusters. The first paper on the globular cluster survey, globules, is out. And there we've studied about 8 plus 3, 11 clusters. 8 is shown here, 3 were already present elsewhere. So we combined all the 11. And you can see that the UVAT has observed the outer regions, while the HST has observed only the central region. And this has helped us to combine the HST and the UVAT data to produce something called a combined Kalamanchy diagram. And this is the combined for the 11 clusters. And you can see clearly the horizontal branch, the post-HB stars, the Bluestraggler stars, and the white dwarfs. Now, we also detect a lot of variable stars. And this is, mind you, even in the crowded fields, compared to the UVAT resolution is about 1.2 arcsecond, and nothing compared to HST. But still, since the far UV stars are very less in number, you can actually be the crowding, and most of the stars are resolved, except in certain cases you can see the very central regions of these clusters are not resolved. So in comparison, this is the Shaivan et al. Paper from Galax, where they put together 23 galactic globular clusters CMD, and you can see that none of the features are coming out properly there. There are two reasons out here. One is they are able to look at only the outer regions of these clusters due to poor resolution. And second, the membership, information was not available. So here we have made use of the membership information as well. They were not able to combine the HST data, whatever is available, because the inside resolution is not enough. But for UVAT, it is enough. So we were able to effectively combine the HST information. And this is in press as of now. So having done so much, and we have all launched Astrocyte UVIT, and we know how to make it instrument and operate it. It's producing wonderful results over the last 6 years. So what is the way to move forward? So with this, keeping this in mind, we proposed in the Indian Spectroscopic and Imaging Space Telescope a few years back to give you a landscape. What is in the offing? We have JWST, we will have Euclid and WFIRST to come by. They're all in the infrared regions. There's nothing coming by in the UV region. That region where India has the advantage of already operating a telescope, there's nothing out there in the international scene, or at least nothing approved and ready to go, or rather getting built as of now. So to put the INSIST progress in a nutshell, the origin of the proposal is in the first UVIT science meeting held in IEA in 6-7 July 2017. It was evident by then that the wonderful images produced by UVIT will produce good science, and lessons learned and the teams which worked for the instrument should be made use to produce the next generation UV optical telescope. So there was a call from ISRO for the future astronomy missions, and since we are already working on a proposal, it was submitted in April 2018. The proposal was reviewed by a subcommittee of then ADCOS, and that committee reviewed all the proposals submitted based on this call, and that committee recommended the seed funding in October 2018. We made a presentation to the ADCOS in December, and by March 2019, the proposal moved to the pre-project phase with some seed funding of 30 lakhs. And the idea was to come up with a proper optical design and science cases, science document, and test out some critical components of the design. So around the same time, we had also discussions with Castor mission, which was actually being planned from early 2010s itself for a larger mission. So Castor, in fact, had imaging requirements. There were no spectroscopic requirements, but INSIST had both imaging and spectroscopic requirements. We had a joint meeting in September 2019, and we realized that we could actually have a joint mission if we could overlap the design and come up with a combined design and understand the work share between the two nations. And we also had discussion with Indian collaborators, their roles and responsibilities, so that we could actually see, how the work can be divided and a responsibility can be shared. We created a complete science document, though we had submitted a science document along with the first proposal, and it was submitted to ISRO in August 2020. And based on that, we are producing a few science papers to be submitted very soon. The Canadian Space Agency sent a letter of interest for collaboration in the project by October. And then we discussed the detailed work share between with India and Canada in November. So we had a year back, we had a first CSA ISRO INSIST Castor meeting, and we in principle agreed to work towards a joint mission. And right now, the Canadian Space Agency is investing in a major study, and they have this is actually out. I had to update this. The phase 0 study is already started. So UVIT and beyond, we had a workshop in the 39th ASI meeting, and we have completed 4 reviews during the pre-project phase, and we look forward to move to the next phase, which is equivalent to the phase 0 of the Castor mission. So they insist the big science questions. You could divide them into two: imaging and spectroscopy. Imaging is like the cosmic star formation, AGN, demographics of star formation in groups and clusters of galaxies, the UV escape from galaxies, etc. And you also can have imaging with respect to the local star formation, local globular clusters, and the galactic science cases. Spectroscopy is basically centered on accretion mechanisms around biasos, chemical and mass assembly of galaxies, chemistry of multiple stellar population in globular clusters, chemical enrichment history of nearby galaxies, etc. Because the spectroscopy done with a 1 meter will only have it may not go deep. So basically it will cater to the nearby galaxy science cases. The operational philosophy will be a combination of legacy surveys of a down selected topics as well as the GI program. So the high-level science cases are a mission duration of 5 years, sun synchronous orbit with a primary mirror of 1 meter off axis. And I will cover this. The spatial resolution we expected about 0.2 arcsecond, which is pretty good. And wavelength coverage from 150 to 550 nanometer. This is divided into 3 bands, UV, U, and G. And we, in the instrument side, we plan to have a photometry. There's a large coverage, about half a degree field. And we also have the same field, we'll have a slitless spectroscopy. We also have a plan for a small area, just like the ECS HST central field, 2 by 3 arc minute, multi-object spectrograph, and then a precision photometric field. So these are the other things. So the MOS will have a resolution about 2000 and DMD sensitivity about 20, and it can have multiplexing of about a couple of hundred stars. That's based on the DMD. Now, if you look at a field, how it will look like, it'll be looking like, you have a 3-mirror anistigmatic telescope with a fold mirror, and then the FSM is sitting here, which is the fine sensor mirror, and the guider, which would actually make sure that we get the image proposed resolution. And then the field is divided into 3. One is the G band, the U band, and the UV band, to make sure that the UV always gets the reflected light. And G band is the one which is used for feedback into the FSM for the image quality. It also will have a precision photometric field. Then the U band, U band will have, this is the U band, sorry, and this is the reflected and again reflected. So one field will have the DMD spectrograph, the other will have the imager. So basically you'll have U band, UV band, and G band imager. And the multi-object spectrographic field, which is their adjacent field, will have an imager so that whatever field you're using for spectroscopy, you can actually see it in the U band and G band as well. So how do these fields look like? So this is the kind of area coverage for the U band, G band, and UV band, and the simultaneous. So you'll be getting images simultaneously over here. And if you want to insert a slitless grism, then you can do that. That is available in the UV and U, but not in the G, because G band has to feed back into the FSM. So slitless mode only in UV and U. And you can see the G band small precision photometry. This is for in case a certain requirement for looking at exoplanet science case, then a specific case can be provided here. And this is the blue field is for the multi-object spectrograph. So if you compare the field with respect to the HST, UVIT, this is the INSIST and the GALAX. So this is the field comparison. Resolution-wise, you can see that the GALAX was like this, UVIT is like this. Now you would actually INSIST would be something like this. So these are covered under various publications which are in the offing now. The multi-object spectrograph is coming from a DMD. DMD has mirrorlets, and then you can actually operate the mirrorlets, and then whatever star falling on this mirrorlet can be actually flipped to a spectrograph, and that you'll basically get the multi-object spectrograph like this. The point is over here, you normally do multi-object spectroscopy using a fiber fed things, so that the light falling on the fiber can be fed into a spectrograph. But then here the fiber, this is UV operating in UV, and also the sampling is at 0.2 arcsecond, which is coming toward a few tens of microns. So you can't have any slits or fiber to cover this small coverage. So these slitlets are actually the DMD mirrorlets are actually ideal. And now these are being pursued for being used in various as the driver in this multi-object spectrographs by various laboratories. And this is being tested, never used in the space so far. And so we will be using it and testing it out and then calibrating it, etc. Right now we have a lab-based model ready, and then we are testing with respect to imaging as well as spectroscopy. In the next few months, we plan to take it to Cavalier and then put it in test it in 1.3 meter JCBT as well. We also have science cases and we have science leads from various institutions. So there are many science cases we have identified, and this is part of a science document as well. And these are participating institutions with respect to science, and there are a lot of topics as well. Yeah, so I stop here. I also would like to point out that we have started working with the Canadian team and in the phase 0 time, and then many meetings are going on. And the Castor, in their long range plan, they actually identified Castor as the high priority project, and therefore CSA is funding it, and they have already started a study worth more than about 13 crore with the industry, Honeywell and ABB. And right now they have initiated the science study, and the science study will go on for another year. And many of the members in the science team are part of the Castor science team as well. So thank you, I stop here.
That's very nice talk covering broad area of UV astronomy. So are you okay taking a couple of questions?
Yeah, sure.
Are there any questions or comments? Yeah. Devendra Ojha is.
Yeah, so I just have one question about this globular clusters.
Yeah.
I mean, when you go to insist, so have you done some simulations? What kind of new populations you can, I mean, expect to detect, or I mean, what extra information will come?
I think you're looking at what extra information will come from INSIST, right?
Yes.
Yeah, okay. So I hope you can see the slide. So here you can see that some of the globular clusters we are not able to resolve inner regions. And though we resolve inner regions in many cases, the massive clusters like the Omega Sun 2808, etc., we have to discard a lot of sources, because there are some multiple sources within. If you check the HST field, you see multiple sources within that same footprint of UVIT itself. So we have carefully selected them and discarded many of them. So even though you can see outer regions are properly resolved in UVIT, inner regions are not. So many objects are yet to be resolved. And we also know that these inner regions harbor the stars which are actually could be peculiar, and also late stages of stellar evolution, like these EHB stars, post-HB stars, and the white dwarfs. And still the burning question being the helium deficiency or helium range in helium stars, which will actually populate the entire range. This is coming from various clusters. If you can see individual clusters, not all clusters will populate the entire horizontal branch. If one has to populate the entire horizontal branch, there has to be a large range in helium production within the globular cluster itself during its formation time. So which is not available. You have to match with the simulations, but yeah, so that is how we are able to put a limit on the helium things as well as the other composition. So the combination of higher resolution for the inner regions as well as spectroscopy using DMD will be able to tell us about what is the actual origin of multiple population in the globular clusters and the kind of population we see in the inner regions of globular clusters. This will be the two key science things which will be able to address.
Thanks.
Bridget?
Yeah. Yeah, so they are collaborating. I mean, the Canadian astronomers are also there for this. So, what is the data sharing policy? Have we discussed with them? Or data rights in general? I just was curious.
Ishu, can you repeat that question? I couldn't
Yeah,
hear it.
since Canadians are also collaborating with us on this project.
Yes.
So data rights, whether we have discussed with them.
Any policy of
Any
data
policy?
sharing?
So, yeah, it's an important point. We have not reached that stage, so we would be defining the science, the policy, the time share, the data share policy, etc. needs to be discussed. It's little too early as of now.
Okay, for the Globular Cluster studies, are there any contaminants expected there? Or if so, what would be the percentage?
Can you repeat it, Jesse?
I would like to know, are there, in this particular plot which you're displaying now, are there contaminants expected there, or they're all some sort of cluster members?
Contaminants are in the plot on the left side. There is no contaminant. They're all members.
So in a given image, do you take all of them?
No, this is actually a combination of several clusters put together. So 11 globular clusters put together, this is coming here. So with the 11, you can actually see that it is falling within the post-HB and the HB, zero-age HB evolution actually. But then of course, you're right, there are a lot of scatter coming here as well as there. So these kind of stars which are lying below the horizontal branch track actually needs investigation. And these are members. These are real scatter. And then reason for real scatter needs to be, I mean, within over here needs to be understood.
Okay, thanks.
I think the question was about foreground contamination. If I understand.
No, the contamination is removed because this is coming from this.
The question was what was the method of removal? If I understood.
No, the contamination.
The scatter is real and the contaminants are removed. The foreground and background are removed.
I thought how like optical and near infrared one does some nearby. So in this case, in UV, how was it removed? I think that was.
Okay, so
I don't know if that was really a question, but I may ask that.
Okay, that's what you asked.
Yeah,
how do you remove the contaminants? What is the method?
The HST gives promotion membership, and the members used are about 90% for the inner regions, and the outer regions Gaia membership is used.
Oh, thanks.
So these are kinematic members from promotion. Yeah.
Is there any specific reason that insist is decided to be 1 meter? Because still it cannot beat HST.
Yeah. So good question. So the idea behind 1 meter is the following. You would like to get sensitivity as I mean, in the sense that the limiting magnitude to be comparable with the LSST, so that you can actually effectively combine the UV data with the LSST passbands U, G, and I think R. So so that you can actually do a lot of science cases. But if you go beyond 1 meter, of course the cost increases, but also the amount of you'll have to get the whole size increases. So the mass and the volume of the payload increases. So you have to look at what kind of a launch vehicle you're looking at, and also facilities for integrating the whole components, testing and integrating the entire system. So we thought that with our experience with UVAT, 1 meter would be kind of a next step where it's not too ambitious, but ambitious enough to get the sensitivity. But with respect to getting the infrastructure and capabilities for testing, integrating, and then calibration, would be okay with 1 meter. So that is the because it's an off-axis primary mirror we are proposing. and beyond 1 meter, it could be quite difficult.
Thank you.
Thank you, Annapurni. Thank you for that wonderful talk, and let us thank her.
Thank you.
Yeah, thanks. Thanks, Bonnie, for the nice talk. So by this, we are near the end of this today's series of talks. So after this, maybe we'll go to 1 meter telescope. We'll have tea and we can visit this facility, and then the dinner is at 7:30. And those who are in Narita, the bus will start at 8:30 in the night. Thanks for being present and the technical discussion.